In lecture 17b of differential equations and linear algebra, we're getting into the heart of abstract vector space theory. Subspaces, linear transformations, spanning sets, some new concepts, linear independence, basis for a vector space, and then some examples, basis for a null space and a column space of a matrix. Really, really abstract, but really, really key ideas. You need to learn how to think abstractly about these things. Examples help, but you need to be able to get beyond examples as well. As in lecture 17a, for some reason the smartboard is not working anymore, and so I can't do my usual underlining and circling, but we will live with it. Maybe it'll be better. All right, let's jump ahead now to the linear algebra slides. Starting with slide 8 here. Oops, not that. From current slide. Okay, here we go. First few slides are a review. Watch 16b if you want to see them with more detail. Let V and W be vector spaces, and suppose T is a function whose domain is V and whose codomain is W. We call T a linear transformation, or a linear map for short, from V to W, if it is operation preserving. This is really different than what we did earlier when we were talking about linear transformations from Rn to Rm. We thought of those transformations in terms of their linear formulas first, and then we verified that they were operation preserving. Here we're using operation preserving property to define the linear transformation. T of alpha u plus beta v equals alpha t of u plus beta t of v for all, upside down A means for all, scalars alpha and beta that are real numbers, and for all vectors u and v in the vector space V. Okay? So you can draw pictures to help you imagine these things, and it's a helpful thing to do. Let's just focus on summations here without bothering with the scalars. Effectively, I'm going to take alpha and beta to be 1. To be operation preserving in this context, when alpha and beta are 1, means T of u plus V equals T of u plus T of V. T maps from V to W. Conceptually, what you can think here is you've got two different vectors, perhaps, in V, boldface U and boldface B, or with little half arrows if you draw them by hand. What we're saying here in saying this equation is true is we're saying we can get to the end result in two ways. We can either add u and v first to get the vector u plus v, and then map that using t to t of u plus v, right there. Or we can get to the same point over here by finding t of u and t of v individually. Say this point is t of u, and this point is t of v, and then adding those vectors, we get to the same point, okay? Now you can't take a diagram like this too literally, okay? It's a conceptual kind of diagram, but even conceptual diagrams can be helpful. You may want to rewatch what I said and rethink about it. It follows from this that t of 0 is the 0 vector. If the input is the 0 vector in capital V, the output will be the 0 vector in capital W. I talked about that in 16b. We say t is 1 to 1 or injective. If u not equaling v implies t of u doesn't equal t of v. Distinct inputs get mapped to distinct outputs. Said another way, if t of u did equal t of v, then we'd have to conclude that u itself was the same as v itself. U and v were equal. Equivalently, t is 1 to 1 if each equation of this form has at most one solution, where v is an arbitrary vector in capital W. There's at most one solution for x. Maybe none, but at most one, no more than one. We say t is onto or surjective if for all points in the codomain, W in capital W, there exists something in the domain, a boldface V in the domain, a vector V, such that t of v gets mapped to W. T of v is W. Equivalently, t is onto if each equation of the same kind of form has at least one solution for x, no matter what v is in capital W. Just very abstract ideas, but you need to get good at this. If t is both 1 to 1 and onto, we say it's bijective, and that would mean all equations like this have a unique solution. What's the kernel? The kernel is the set of everything in V that gets mapped to the 0 vector in W. Redraw this. Here again is V, here again is W. T maps from V to W. Somewhere W has a 0 vector. the kernel is a subset of V. It could be trivial. It could just be the zero vector. But it might not be. It might consist of non-zero vectors. It's all the points that go to the zero vector over here. And if it is more than just the zero vector, that would mean T is not one-to-one. If the kernel is non-trivial, T could not possibly be one-to-one. Read this as the set of everything in V that gets mapped to the zero vector. And it is a subset of V. The image of a subset of S under subset S of V under T is the set of all outputs as the inputs vary over S. So I can start with some other set here. It doesn't have to intersect with the kernel at all. Some other set. What's the image? It's the set over here in W that all the points in S get mapped to. That's S. This is T of S. I'm not literally plugging the set into the function. I am finding all the outputs as the inputs range over S itself. The overall image of T is when S equals V. You can write T of V. You can also just write Im of T for image of T. Examples. If A is an n by n matrix, then its corresponding linear transformation defined by T of x equals A times x has domain Rn and codomain Rm. It takes n-dimensional vectors as input, gives you m-dimensional vectors as output. A is m by n, x is n by 1. So the answer's got to be m by 1. A times x represents an m-dimensional vector. Is it one-to-one? Is it onto? We need to use, it depends. We need to use actually row operations to help us figure it out. And that's part of what we're going to think about with the example at the end of this lecture. Here's a more abstract kind of idea, kind of example. Let C of A comma B be the vector space of all real-valued continuous functions of a closed interval. I didn't really explain why that was a vector space last time, other than just to say you can add functions, you can multiply them by scalars, and the commutative property holds and that kind of thing. But there really is something else that should be mentioned here, and that is the fact that if you add two continuous functions, you still get a continuous function. A fundamental fact from calculus, okay? That is necessary to verify that that closure is satisfied. C1AB is the vector space of all real-valued continuously differentiable functions on the same interval. They're differentiable, they have a derivative, and that derivative is continuous. You add two such functions, it will be another such function. You know that when you add two differentiable functions, the result is differentiable, and if that result in both cases is continuous, when you add those, it will be continuous. When you add the originals, it will be continuously differentiable, I should say. The mapping here, the linear transformation, takes an arbitrary function that is C1, that is continuously differentiable, and maps it to its derivative, which is guaranteed to be continuous by our assumptions. Is a particularly simple linear transformation in this context. This is a linear transformation between function spaces. The domain and codomain are sets of functions. The points themselves in these spaces are functions. What? Points are functions? That's the way we're thinking of them. We're thinking of them as individual entities, and we call them points in this context. There are other similar kinds of linear transformations involving the derivative that are related to differential equations. For example, if I define T of f with the same domain and same codomain to be f prime plus 4f, the kernel of T would be the set of all solutions of a differential equation. A homogeneous linear differential equation. In fact, where the left-hand side is essentially this, except let's go ahead and use our Leibniz notation here. Oops, first derivative. dy dt plus 4y equals 0. The kernel of this linear transformation would be all solutions of this differential equation. Think about how it matches. F prime goes with dy dt, 4f goes with 4y. The kernel is everything that gets mapped to the zero function in this case. So thinking of that as a zero function on the right-hand side, the kernel is the solution space. That's a relationship to differential equations. A similar kind of example is this. If Pn is the vector space of all polynomials of degree less than or equal to n, define a linear transformation from Pn to Pn minus 1 by this formula. This is essentially differentiation, except restricted to a domain that consists of polynomials, not just arbitrary, continuously differentiable functions. Though polynomials are continuously differentiable, Pn would be a subspace of C1. That would be true. But I'm restricting the linear transformation to just this particular domain. One interesting thing here to consider is if we let n be 2 here. Actually, when I write this by hand, I'm going to do sort of a double struct P. If we let n be 2 and consider this mapping, sending this quadratic to its derivative, really, a1 plus 2a2x, I want you to realize that this mapping actually can be implemented using a matrix multiplication. Because really, in a sense, the powers of x are just placeholders. This is analogous to the linear transformation, I'll call it S, taking a three-dimensional vector, column vector with components A0, A1, and A2, and mapping it to, well, I'm going to go ahead and write it as a two-dimensional vector, a vector A1, 2A2. Just focusing on the coefficients of these different powers of x, a zeroth power, a first power, and a second power. It's analogous to this linear mapping, which could be implemented with a 2x3 matrix. Because S maps from R3 to R2, it would be a 2x3 matrix. You may want to see if you can figure out what that matrix is. It's not that hard. So even though this is a more abstract kind of linear transformation, it can be related to the linear transformations that we've been talking about. And that is going to be a big thing for us. Fundamental definitions and facts. If T from V to W is a linear transformation, let's assume that V and W are vector spaces when I write that. Then the kernel of T is a subspace of V, and the image of T is a subspace of W. In fact, with the second one, you can say the image T of H of any subspace H of V is a subspace of W. That's a mouthful to try to think of all at once here. Again, pictures can help. I already drew the picture for the kernel. We could consider some subspace H of V. It gets mapped to its image T of H in W. If H is a subspace of V, then T of H will be a subspace of W. Okay? How would you prove this? You want to use the subspace test. Think about it in the kernel case. How would you prove the kernel of T is a subspace of V? You want to first verify it's non-empty. Well, that's easy, because we know T of 0 is 0. The kernel always contains at least the 0 vector. Is it closed under addition and scalar multiplication? Those are the other two conditions of the subspace test. Suppose U and V are in the kernel. Is U plus V in the kernel? Yes. Why? Think about it. It's because T is operation preserving. This is T of U plus T of V, and if I assume U and V are in the kernel, these are both 0. So the answer is 0, and therefore U plus V is in the kernel. And it's closed under scalar multiplication. If alpha is a scalar, T is operation preserving, because I'm assuming it's linear. I still get the 0 vector. So alpha times U is also in the kernel. That's a quick outline of the proof that the kernel of T is a subspace of W, or V, excuse me. If you're doing the actual proof, you want to give an argument, you want to write it in complete sentences, but that's the key idea there. This means if A is an n by n matrix, then the null space of A is a subspace of the domain, Rn, of the corresponding linear transformation, and the column space is a subspace of Rm. The null space is all the vectors such that A times x equals the 0 vector. The column space is the set of all linear combinations of the columns of A. It's really the span of those vectors. That's going to be a subspace of Rm. It's equivalent to an image of T. Another theorem. If T is a linear transformation, then T is 1-to-1 if and only if the kernel is 0. That's related to what I was mentioning a couple minutes ago, though it's not a complete proof. That's a theorem. You should think about proving that. I didn't talk about it last time. Here's a definition. If T is a linear transformation, then T is onto, if and only if the image of T is all of W. That's nothing to prove there, that's a definition, but it's worth stating. Note, we know that a function will be invertible if and only if it is both one-to-one and onto. It's also called bijective. I mentioned in lecture 16b that the real key condition is one-to-one. Onto can be, if it's not onto, it can be gotten around by shrinking the codomain. But I said we're not going to worry about that anymore, and we really are not going to worry about that anymore as far as I know, looking ahead. So we will want a function, a T like this from V to W, to be bijective if it is both one-to-one and onto with the given codomain. A theorem, then, is that the inverse function of a bijective linear transformation from V to W is also a linear transformation, but from W back to V. Okay? I actually did prove this, or gave the outline of the argument for this, in the case where V and W were Euclidean spaces. You need the operation preserving property of T to prove that T inverse is operation preserving. You also need the fact that T inverse is the inverse of T. Okay, I did prove that back there. I would encourage you to look and think about it on your own here. Here's a definition. If T from V to W is a bijective linear transformation, so it's a linear transformation that's both one-to-one and onto, bit of terminology, we say that V and W are isomorphic vector spaces, or just isomorphic for short. We also say that T is an isomorphism, and we write this. V, what's that thing? Approximate. This does not mean V is approximately W. It can be taken to say V is maybe equivalent to W or similar to W, are words that are typically used. It's not that I'm trying to approximate one vector space by the other, though they do act in similar ways. Okay? And it's the operation preserving property of linear transformations that verifies that. Essentially, all algebraic properties of V are shared by W and vice versa. I can prove things related to that right now. It's just for your own edification now, and it'll come back some later. More. Lots of abstract stuff here. Hang on for the examples at the end. Let V be a vector space, and let S be a non-empty subset of V. S could be finite, it could be infinite. Okay, I'm not specifying that ahead of time here. Span of S. We did define the span of a finite collection of vectors before. The span of a finite collection of vectors was the set of all linear combinations of those vectors. So this definition that I'm saying here does apply and gives it the same thing when S is finite. But this still works when S is infinite. S itself may be an infinite set, but the span of S is the set of all vectors in V that are finite linear combinations of vectors in S. We want to emphasize finite linear combinations because we don't want to deal with infinite sums, because then we'd have to worry about convergence and that kind of thing. Though you can worry about such things if you want. But we're not doing that. So the span of a set S, whether it's finite or infinite, is still the set of all vectors that are linear combinations of the vectors in that set. And as long as S contains more than the zero vector, and S doesn't have to contain the zero vector because it's not a subspace, then this will be an infinite set. Here's a theorem. Same setup, let V be a vector space and let S be a non-empty subset of V. Then span of S is a subspace of V. This is a theorem that I mentioned for the finite case before. And you can prove it with the subspace test. In fact, you can also say that span of S is the smallest subspace of V containing all the vectors in the set S. Once again, pictures can be helpful, though they are not the end-all be-all of this stuff. You need to be able to think at a symbolic level too. This is V. This is S, not necessarily a subspace. Could be a finite set, which for sure would, if it was more than the zero vector, for sure would not be a subspace. Whatever subspace of V containing S is the smallest such subspace, that will be the span of S. In other words, if you had some other subspace of V that contained everything in S, the span of S would be a subset of that bigger subspace. Say that again. The span of S can be thought of as the smallest subspace of V, so this bigger black circle is a subspace of V, containing all the vectors in S. In other words, if you had a subspace of V that contained everything else in S that was not equal to the span, it would be literally bigger. The span of S would be inside the blue oval. It's worth remembering. Definition here is of spanning set. Let H be a subspace of V. If H is the span of S, for some S, I'm not saying what S is, then we say S is a spanning set for H. And this means every vector in H can be written as a finite linear combination of vectors in S, because that's what span means. If H equals the span of S, I'm just saying essentially what this means. Call S a spanning set, and it does mean, by the definition of what span means, that everything in H can be written as a finite linear combination of vectors in S. Note, we are very interested in minimal spanning sets, making S, in a sense, as small as we can get away with. This is the motivation for the content that we are about to explore right now. Linear independence and basis. Very key concepts. Seems like abstract math is nothing but definition, theorem, maybe some proofs thrown in. It's hard to stay awake, isn't it? Especially if you're watching this at 3 a.m. or something. Let V be a vector space. This is a definition, it's not a theorem. Suppose you've got a finite subset of V. This is like an S, but it is going to be a finite set here. We say that this set is linearly independent, or we say it's a linearly independent set, or we say these vectors form a linearly independent collection if the only solution of this vector equation, where this linear combination equals the zero vector, and the scalars x1 through xn are unknown, so to speak, we're looking for solutions of this, if the only solution of that is the trivial solution, where all the x's are the number zero. Notice this zero is bold-faced, that's the vector zero. This is the number zero, it's not bold-faced. And you can think of these in terms of column vectors, but you don't have to. This still makes sense in the abstract. We could be talking about a function space here, and v1 through vn could be a bunch of functions, like cosines and sines, etc. But we get a linearly independent set if the only solution to that is the trivial solution. This is equivalent to what I mentioned linear independence means in the case of two vectors. I've said linear independence in the case of two vectors means, in the case of two non-zero vectors, that neither is a multiple of the other. Neither is a scalar multiple of the other. If that did not hold, if you had V to be some scalar C times W, that would not be a linearly independent set of two vectors. It would be a linearly dependent set of two vectors. That equation would be equivalent to saying 1 times V plus negative C times W is the zero vector. And x1 equals 1 and x2 equals negative C would be a non-trivial solution of the equation like this. So it would not be linearly independent, it would be linearly dependent. So this is equivalent to what I've said before for the case of two vectors. If V happens to be Rm, m-dimensional Euclidean space, then equivalently this collection of vectors is going to be linearly independent when the null space of the matrix is zero, where A, the matrix, consists of all of these vectors as its columns. Say that again. If these vectors, v1 through vn, are in Rm, they are m-dimensional vectors, and you make a matrix whose columns are those vectors, thinking of them as column vectors, then they are linearly independent when the null space of that matrix is the zero vector. In other words, the kernel of the corresponding linear transformation is just the zero vector. Same situation, if m is less than n, if the dimension of these vectors is less than the number of vectors, there's no way the set can be linearly independent, because the null space would be more than just the 0 vector. If you did row operations, when m is less than n, when you have sort of a long skinny matrix like this, and you were trying to find the solution set of the corresponding homogeneous equation where you have all zeros on the right hand side, then you will get some free variables when you do row operations. And that means the kernel is going to be non-trivial. Okay, so if the dimension of the vectors in Rm is less than the number of vectors, there's no way it can be linearly independent. It must be a linearly dependent set in that case. Another definition, perhaps the most important definition in the class here. Does that get you motivated? Let H be a subspace of a vector space V. A finite collection of vectors, I'm going to just consider a finite situation here. V1 through Vp, I'm going to call this set beautiful curvy B for basis. I didn't have to make it that way, but it's just so beautiful I couldn't resist. Is said to be a basis for H if two conditions hold. One, B is a linearly independent set. These vectors form a linearly independent collection. The only solution to this kind of equation, where I plug in the V1 through Vp in place of V1 through Vn, is the trivial solution. All the x's have to be the number 0. And B spans H. Everything in H is a linear combination of the vectors in B. If those two conditions hold, then we say B is a basis for H. Okay? The idea of a basis is a real key idea. For one thing, because it's going to make clear the idea of dimension of a vector space. The dimension of a vector space, when it's finite dimensional, when it's got a finite basis, is going to be the number of vectors in any basis, actually. Any two bases of the same vector space or same subspace have to have the same number of elements. And certainly, like thinking in R3, for example, take a line through the origin, if that's your subspace, it's going to have a basis with one vector, any non-zero vector on that line, parallel to that line through the origin. A plane through the origin, it's two-dimensional, it's going to have a basis of two vectors. Any non-zero vectors that are not parallel are going to be both linearly independent and span the plane. You can generalize that to higher dimensions. These basis vectors will be the basis, pun intended, for coordinate changes to new coordinate systems, for example, skewed coordinates or rotated coordinates that we talked about way back in lectures 1 and 2. And I said was the most important application of linear algebra to differential equations. We're getting close to that. Something called the spanning set theorem says that if S consists of vectors v1 through vn, why did I pick a p here instead of n? I could have picked an n. Just change the notation. Now I'm going back to n. I've got a set of n vectors. It's a subset of a vector space, and I'm letting H be the span of those vectors, which means H will be a subspace of V. Then, two things can be said. If one of the vectors in this collection is a linear combination of the others, then removing that vector from this set still results in a spanning set for H. Still results in a set that will span H. I'm trying to head toward that minimal spanning collection. And if what's left over after you remove that one vector still has the property that one of the vectors in there is a linear combination of the others, you'll be able to move that other vector as well. You'll still continue to be able to make it smaller until you get to a situation where none of the vectors are linear combinations of the others. If H is not the trivial subspace, just the zero vector, then some subset of S must be a basis for H. If S spans H, it's not necessarily a linearly independent set. By removing enough vectors, you can make it into a linearly independent set, and therefore it will be a basis for H. By the way, I didn't type it in the PowerPoint here, but any collection of vectors that contains the zero vector in it will automatically not be linearly independent. It will be linearly dependent. For example, if Vn happened to be the zero vector, there would be a non-trivial solution to this. I could take the xn to be anything, as long as the other part of the linear combination was equal to the zero vector. I could take all the other x's to be zero, in fact, in that case. And another comment worth mentioning is the zero subspace, the trivial subspace with just one element, has no basis. And that means it's actually zero-dimensional. Makes sense? All right, this is our last slide. I will show you a little bit of Mathematica, symbolic this time. We want to calculate a basis for the null space and the column space of a given matrix. I'm going to take this example and talk about how to do it for this example, but the comments that I make for this example do generalize to other examples. So focus not only on the calculations, many of which you'll actually need to check if you want to, but also just in the big picture of what I say. So it's an example. We're going to find a basis for the null space of a matrix and also a basis for the column space of this space of that same matrix. Equivalently, we're going to find a basis for the kernel of T and the image of T for the corresponding linear transformation T, defined by T of x equals A times x. A is this matrix, a 4 by 5 matrix, 4 rows, 5 columns. I'd have to multiply this by a vector on the right that would have to be 5-dimensional. And the output would be a 4-dimensional vector. That's a linear combination of the columns, in fact. As a linear transformation, or the corresponding linear transformation would map R5 to R4, a bigger space to a smaller space. 5-dimensional space to a 4-dimensional space. I think I forgot to mention, maybe I did mention this, if your subspace is not just the zero vector, there are always infinitely many bases for the subspace. Writing the solution set of the corresponding homogeneous system in parametric vector form will automatically produce a basis for the null space. I got to explain that a little bit more. Furthermore, the pivot columns of the original matrix form a basis for the column space. What were pivot columns? They were columns of the matrix that correspond to leading ones in reduced row echelon form. Either way, doing row operations, doing row reductions is the way to go. Now I'm just going to tell you the answer, the final answer after row reduction to reduced row echelon form here. The intermediate calculations are something you might want to still do. You might want to still practice these things. Here it is, calling the end result B. I didn't have to give these names, but I did. This is the reduced row echelon form of A. And by the way, reduced row echelon forms of any given matrix are unique. We have leading ones in rows 1, 2, and 3, nothing in row 4. We have leading ones in columns 1, 2, and 4, not in row 3 or column 3 and 5. The pivot columns are therefore columns 1, 3, and 5, or excuse me, 1, 2, and 4, excuse me. And that means a basis for the column space, I'm just telling you how to do it without explaining, consists of the 3 vectors that are in the first, second, and fourth columns of the original matrix. What about the null space? Remember, these things do represent systems of equations. Though these are not augmented matrices, I could have considered augmented matrices. In thinking about the null space, I'd want a column of zeros over here, and I'd put a dashed line between the main matrix and the last column of all zeros. However, when you do row operations and you've got a column of zeros, they all stay zeros. So you don't really need to write it in that case. You do if they're not all zero. The original system of equations was x1 minus 3x2 plus, excuse me, x1 minus 3x3 plus x4 plus 2x5 equals 0. Then x2 minus 4x3 minus 3x4 plus x5 equals 0. Negative 3x1 plus 2x2 plus x3 minus 8x4 minus 6x5 is 0. 2x1 minus 3x2 plus 6x3 plus 7x4 plus 9x5 equals 0. And the row reduction algorithm to this matrix gives us the following equivalent system. x1 minus 3x3 plus 4x5 equals 0, pretending I got an augmented matrix with zeros in the rightmost column. The next line gives you x2 minus 4x3 minus 5x5 equals 0. And the third one gives you x4 minus 2x5 equals 0. The last line just says 0 equals 0. You don't need to write it down. We can solve these equations for x1, x2, and x4 in terms of the free variables x3 and x5. For x1, I have to add 3x3 to both sides to get a positive 3x3 and subtract 4x5 from both sides to get a minus 4x5. For this one, I need to add 4x3 and add 5x5. And for this one, I need to add 2x5. So the biggest mistake people make here is forgetting that I really do have zeros over on the right, so to speak, and I get equations with zeros on the right, and I need to solve for the variables corresponding to the leading ones in terms of the free variables. So I need to add numbers when they're negative to both sides, and I have to subtract numbers when they are positive to both sides. Look at this. In vector form, as a 5-dimensional vector, treating x1 and x3 as free, I could write an arbitrary vector in the null space as x3 times 3, 4, 1. Don't forget the 1 because that corresponds to x3 itself. x4 doesn't depend on x3, and x5 doesn't depend on x3. 0, 0. Plus the next free variable, x5, times the 5-dimensional vector whose first component is negative 4, second component is 5, third component is 0, fourth component is 2, and fifth component, corresponding to the fact that x5 equals itself, is 1. And it's going to be those two vectors that form a basis for the null space. 3, 4, 1, 0, 0, and negative 4, 5, 0, 2, 1. Those two vectors are linearly independent. They're not scalar multiples of each other, so that's just the simpler case. And they span the null space. Why? Because of the solving that it did. An arbitrary vector in the null space can be written this way, where x3 and x5 can be anything. So the null space is two-dimensional. How about the column space? There were 3 pivot columns, columns 1, 2, and 4. Those same columns, thought of as column vectors, here, here, and here, form a basis for the column space. You see those vectors there. 1, 0, 3, negative 3, 2. That's this one. 0, 1, 2, negative 3. That's this one. And 1, negative 3, negative 8, 7. That's the fourth column. Because those are the pivot columns, which you can see by being in reducer or echelon form. So the column space is 3-dimensional. Interesting. If you add the dimensions of these two, 2 and 3, to get 5, it's the same as the number of columns in A. That's no accident, actually. That will always happen. So once again, I've got a 5-dimensional space mapping to a 4-dimensional space. The subspace of our 5 that gets mapped to the 0 vector consists of a plane in 5-dimensional space spanned by these two vectors. You can only imagine that by analogy. And the image of the linear transformation. The column space of A is a three-dimensional subspace of four-dimensional space. Somehow it's like ordinary space sitting inside a fourth dimension. Yeah, you can only imagine that by analogy. All right, let's end by looking at Mathematica a little bit. RowReduce does row reduction to reduce row echelon form. MatrixForm makes the output look like a matrix. There's the B matrix. Here I did add a column of zeros just to emphasize I can think about the augmented matrix, and you see that the RowReduce form still has a column of zeros on the right. I'm not going to show you the details of all this code. I'll let you look at that on your own if you want to download the notebook off the Google Drive. But this bit of code here, here, and here, etc., that involves what I talked about briefly in lecture 16b related to doing row operations by left multiplication by elementary matrices. So watch the beginning of lecture 16b if you want more detail on that. Have a good day.